So let us start. We have to revisit what we did 2-3 weeks ago. So what we have covered is this red-black tree data structure, which is the only balanced BST that we have. Well, not balanced, but this is the only BST that we have seen where insertion, deletion, search is everything is log n, where n is the size of the tree. But it may not be balanced in the sense of difference of height that we had defined. Still, it will give us log n time maintenance algorithms. So we did insertion and deletion. Any questions till now? In fact, in the mid-sem, you had to apply this deletion algorithm also. So this is the theorem we have done, that we can do search, insertion, deletion. We can find the minimum in the tree, we can find the maximum in the tree, everything in log n time. Moreover, if you are given a pointer to a node in the tree, let's say element x, then you can find the predecessor and the successor of x also in the same time. Do you see why? So this pseudocode we have not written anywhere, but you can do this as an exercise. So in general, for a BST, when you want to find the predecessor of a node, you don't have to take more than height time of the tree. In this case, the height is log n. So overall, this will be log n time. So for predecessor, you just have to, sorry?
First of all, we have to go to left child, then right child.
Yes. So predecessor is kind of, you think of searching for an element which is less than x, right? So whatever path in the tree the search will take, roughly the same path you will take to find the predecessor. So everything can be done in the height of the tree, same time as search. Okay, you will not need to look at all the elements, but only the ones you do for a search operation. So that pseudocode is not hard, you can do that. So you can write the pseudocodes for, actually how did you find min in the RB tree? That pseudocode also we have not written, I think. How do you find min in the tree? Yeah, but will you necessarily find everything on the left? Sometimes you might have to go right? There may not be a left child. Will you need to go right in this case? Yeah, so for the min, you don't need to go to the right because if you go right, then you get an element bigger than the parent. So you can keep moving left, and for max you can keep moving right. For predecessor, it may be a zigzag. You might have to go left and right, depending on the data. So it's better that you practice this. Okay, so these 4 ones you have written, then in search, insert, delete you have seen already. So then you will have all the operations in log n time. There are more operations which can be done in log n time. Maybe I'll mention these in the assignment. So right now what we will do, since you are fresh from our exam week, we can warm up with some things that you already know, right, which is the divide and conquer paradigm. So let us warm up with some examples of that. So this paradigm you have seen in many, many examples by now. In fact, binary search itself is kind of divide and conquer. You are dividing it into half. And we have done many algorithms now, data structures also, which use recurrence. Recurrence again is an example of divide and conquer paradigm. So let us continue on this, and then we will start a new topic. So let's revisit this paradigm. With some more interesting examples. So we'll see three interesting problems which you may or may not have seen before. So first one is maybe just a line about what is divide and conquer. So this is the paradigm is what? What do you do here? You have to divide into a smaller instance of the same problem. And then from the smaller instance, you have to solve the bigger problem. So your input, you convert it into a smaller one. And then you go back. Right, so the first part is the divide part. You divide into smaller inputs. Smaller inputs meaning that input has become smaller, but the problem is the same as before. Assuming, so you assume that you can solve smaller inputs. You can solve the problem on smaller inputs or smaller instances. And once you have solved them on 2 or 3 such inputs, then you combine that solution to get solution for the given input, the bigger input. Right, so the last part is the conquer step. What is the famous example which you have seen already in programming course? Yes, so kind of the only algorithm for sorting that you have seen with a proof of n log n is merge sort. Have you seen any other sorting algorithm of this complexity? But was there a proof of n log n? So that doesn't really work in n log n. So quicksort is more of a heuristic. Only provable algorithm you have seen is merge sort. So there you divide your array by mid. So you will look at elements that are smaller than mid and bigger than mid. Well, or you can just in the array you look at the n by 2th entry and sort the array before that and sort the array after that, and then you merge. Right? So the first 2 operations come in the divide part, and then you have to merge, so that is the conquer part. So this will be the format of your proofs also. When you give the pseudocode, you have to do this. So give the divide part and give the conquer part. Okay, so let us see this now on a new problem, which is half majority. So this is the problem of given an array having n elements, which may or may not be integers. They may contain anything to the extent that the elements may not even be comparable. Okay, there may not be a comparison operation. So an array of a collection of elements or a list of elements is given, and what you have to find is whether there is an element that appears with frequency more than n by 2. Okay, so this is the half majority. It's not the election majority, because in election majority nobody may have gotten more than 50% votes. Right, so this is why we use half majority. So here you want to check whether somebody got more than 50% votes. Okay, that is the problem. So the input is a array. So obviously it is unsorted because there may not even be a way to compare elements.
Which means we have different data types, right?
Can be anything. It can just be array of several structures. Structures themselves contain other things. So you cannot compare two structures, but you can still say that this structure is same as that structure. So there is only equality operator. There is no, I mean, there may be, but there may not be a comparative operator. And it's not needed in the problem because the problem is only about frequency, more than 50%. So in the output, you have to say or you have to output an element x that is with frequency so let's just shorten this to x such that the frequency of x in A is greater than n by 2. So you have to output this element, some element which has frequency more than n by 2. If it doesn't exist, so for example, there may only be 3 elements, each with frequency n by 3, right? 1 with n by 3, 2 with n by 3, 3 with n by 3. So in that case, there is no half majority, which happens in elections. If there are many parties, each of them may get just smaller than 50% votes, right? So when that happens, you have to say that there is no half majority. So what is the fastest algorithm for this? So how will you solve this problem in a competitive programming situation? Sorry? Log n.
By p would be the number of p.
That is very bold. It's impossible to solve this below n steps. Because how will you even if I give you x, how will you verify that the frequency is more than n by 2? You will need to check n by 2 elements, entries in the array. N by 2 is an obvious lower bound, but what is an upper bound? What's an algorithm?
Sorting and taking median.
Yeah, so if the elements have a comparative operator, then you can sort. And then you can take median or whatever, right? So that will be n log n algorithm.
And if we get a sorted one, then we can get it down to log n by
Yeah, but as I said, there may not even be a comparative operator. So what will you do in that case?
we can count the number of each types.
Yes, so that will be how much time? Order n. No. Each element you have to count the frequency. So n times what?
But if there are n elements,
N times n. So the first idea here will be find the frequency of each element. So for all y in A, find the frequency of y in A, right? So this is order n square time. Is this clear? This is actually no idea. This is just the brute force. This is idea 0. Okay, just by definition of the output, what you want, you just compute each and every possible frequency. So that will be full scan for every element. So that's order n square. If you can sort if sorting is allowed by the array or by the element, by the universe of elements, then you can do in order n log n. But what we want to do in this class is we want to solve this in a single scan. Okay, not only order n, but we want to just scan this array once and find the majority, half majority. Have you seen this algorithm? How do you think it works? So this is a very clever algorithm. It's actually incredible that such a thing exists. Okay? Right. And when will you update the element? So you have seen this before then. Yeah, so even when he told you, you may not be convinced that it will work. So we have to break it up into some observations and then give this pseudocode that was just described. So some of the observations are, what you observe is that so if you select two unequal elements and drop them, so let me say not select, but dropping two unequal elements from A or deleting. So if two elements are unequal, then you can delete both of them from the array. So the array becomes of size n minus 2. And the claim is that half majority is preserved. If x, element x was half majority or value x was half majority before, after deletion of these two, it remains half majority. Do you believe this? So simple example is, so alpha is an element, then beta, gamma are elements. They are different elements. And again alpha, and let's say delta, and maybe another alpha. Okay, so I'm thinking of them in pairs. So I have 7 elements. They are alpha, beta, gamma, delta. It can be anything. These can be structures or whatever, trees. Okay, they may not be numbers. So you can only compare them in you can just do equality check. You cannot do comparison. So if I drop beta and gamma, so initially is there a half majority element in this array? Which is? Right. So now when you drop beta, gamma, what is the half majority? Continues to be alpha, right? And then you can drop alpha, delta because they are different. And you see that now you have only alphas remaining, so obviously it is half majority. So the size of the array keeps reducing, but within that sample size, half majority is still alpha. Right? And you can see the proof of this. In this example, from this example, you can give a proof. So,
Sir,
yes.
but if there is some other thing in place of alpha,
Yeah.
then alpha will not be half majority.
For example, what? The first two elements are what?
Both are alpha. If we take one alpha, something else.
Yeah, so you can take, like we did, you take alpha and delta, delete both of them.
Yeah, but then alpha will be only 3.
Right. Sorry, it is half majority. When you delete two elements, the sample size reduces to n minus 2. So from 7, it becomes 5. And in 5, you have 3 alphas, so that is a half majority. Yeah, so you have to, you have to do the proof properly. Don't get convinced too fast, so you have to show that when alpha was a half majority, it remains a half majority. And if there was no half majority before, then after deletion also there is no half majority. Right? You have to prove both sides. So you have to do that. So do it at home. Show that half majority in A, if and only if half majority in the deleted A.
And half majority means greater than 50% or greater than equal to 50%?
No, no, no. Let's take strictly. Although it should not, the result should not change, but let's take strictly greater.
Sir, I can make an example in which if we consider greater than equal to, then it is not.
Perfect. So then we have the correct definition. So we stick with strictly greater than. Okay, so that is the first property. That half majority may or may not exist, but whatever the case, when you go to the new setting, after this deletion of two unequal elements, the property is preserved.
सर ये बताओ कि इसमें जो अल्फा है, फर्स्ट में दो अल्फा है, इनमें से भी हम एक अल्फा को कुछ मान लेते हैं, कुछ लैम्डा कर देते हैं, तो फर्स्ट
But that is a different array then.
यस सर बट
So then we have to draw that example.
यस सर
So what is the example?
सर अल्फा
Yeah.
लैम्डा
Hmm.
बीटा गामा अल्फा डेल्टा एंड अल्फा देन सर
Then there is no half majority.
बट सर इफ वी डिलीट लाइक फर्स्ट थ्री पेयर्स देन अल्फा विल रिमेन एंड इट इज हाफ मेजॉरिटी इन वन साइड
You are saying half majority will appear.
या आफ्टर डिलीटिंग
Yeah, that is actually true. Hmm. That's a good point here. Obviously, in the end, if you have just one element, that is half majority. So what should we do here?
But that is very specific. If I add one more element at the end, say psi, then no half majority exists.
So we should probably be looking at pairs then only, not single element in the end. Okay, so let us just add another alpha here. Let us talk about pairs only. So we deleting two unequal elements in A, and we are assuming that there are m pairs.
So, but the new example doesn't have any majority.
यस सर
No, his point is that there was no half majority, but when you delete, it appears.
सर बट इफ वी ऐड वन अल्फा टू आवर एग्जांपल
Yeah,
then we got like 2 alpha at the end
yeah,
and it is half majority.
yes.
But according to our definition, it is not half majority because it contains only 4 alpha and the number of elements is 8. So it
Number of elements is 8, and there are 5 alphas.
but sir, in our examples, it is 4 only.
The first example.
No, in second.
In second example, we have not completed it. That just, I mean, the example stops here. So that's the example 2. Example 1 is this. Example 2 is this.
Sir, in our idea,
Yeah.
we are only eliminating unequal elements.
Yeah, yeah.
Sir,
From
मतलब
there we can't eliminate alpha and alpha.
No, no, no. We are not deleting alpha, alpha. The example 2 suggestion was you delete alpha, gamma, beta, gamma, alpha, delta, and then you have just alpha, which is half majority.
sir, it is
And yeah, this problem continues actually.
yeah, sir.
So it's not solved. Let me then only claim this about.
No, sir, that is purely our luck based because if there are odd number of elements and if we are taking it in pairs,
Yeah, yeah, but I don't want to claim now that what I was claiming before. So I have to now make it more precise. Let us just say X is half majority. In A old, then X will remain half majority. I don't want to claim anything more than this. same half majority continues. And we can, for arguments or whatever, for this pseudocode sake, we can just continue with M pairs. So think of elements as pairs, and we delete 2. And then you can easily see the proof that half majority continues.
So this is still a contradiction.
Which one?
Because we have used if and only if. So in example 2, alpha still remains.
Yeah, that's true. Yeah, that is just a typo. It's just one-sided.
But sir, in example 2, if alpha were between beta and gamma, another alpha, eighth element.
You are making another example. To what purpose? What is the claim?
In the second example,
Yeah.
there is an alpha between beta and
No. Give me the problem in the blue statement. Don't give me an example.
But removing the pairwise elements,
Yeah.
it doesn't remain, that doesn't remain any majority element.
No. If X was half majority, it will continue to be half majority.
But it doesn't in my.
No. It's a mistake. You can prove this.
So we should base it upon the number of elements we have. Either it is odd or
No. This you can prove. Just think about this. And what do we do with equal elements? So with equal elements, we will. So once you have gone through this process of pairing and then deleting those pairs which have distinct elements, what is left? Now, the pairs that are left, in every pair, you see repetition, right? Like if you drop beta, gamma, and alpha, delta in example 1, then you have 2 pairs. In every pair, you have a repetition. So naturally, you should just club the 2 into 1. So the first pair, you should see only 1 alpha, club the 2, and in the second pair, you may have alpha prime, club the 2, call it alpha prime. So the elements are halved without changing anything. Because if 2 elements are appearing together, then you should just club them, and all the pairs have this property. So it's an unnecessary repetition, so that is what we should do next. So when all the pairs are duplicates, so then you can reduce each element to single. To the respective singleton. Right, so the example 1 again will become, so now the first pair has become just alpha, the last pair has just become alpha, and these have become empty. Okay? So these are the 2 operations on the array. So the output of this is, or the consequence of this is that n elements have been reduced to half or less. So 1 and 2 halve the elements. So which is basically that A new size is less than equal to half of A old. Fine. What do you do now? So this part of the pseudocode is clear. What do you do next to get to half majority? Well, then you repeat this, right? So you have halved, then you repeat again, you will make 1/4 and so on. So that will be your time complexity. So time and hence also space is order n plus, or let me not put order here, just n plus n by 2 plus n by 4, which is less than or equal to order n. Okay, you get the geometric progression of half ratio. So this will be, this sum is at most 2n. Is that clear? So this is the full pseudocode. Well, it's not quite full because what you have to show, so in the, or what we have shown is that if you had a half majority, then in the end you will output it correctly. But if you output an element saying that it's half majority, is it actually half majority? Yeah, so there is a problem in the pseudocode. How do you correct this?
So we will find the end result and then count its frequency.
Exactly. So you have to add one more part in this pseudocode. When this, in the end of this repetition, when you get x, you should not output this as a half majority already. You should actually verify. So you go back to the original array and check the frequency of this element. If the frequency of x is more than n by 2, then you say that it is half majority. Otherwise, you have to say there is no half majority. Okay, so that's the last thing. So the third observation is that check the frequency of x in A greater than n by 2. And so if yes, or you can say yes, if the check passes, else you have to say that A has no half majority. Okay, so this is the full algorithm. Is this clear? So the proof of this you can work out as follows. If there was a half majority, well, half majority element, can there be two kinds? There cannot be. So there is a, if there is one, that's unique, right? So if there is a half majority in A, then it is unique. Let's call it X. In the end of the pseudocode, X will survive. And not only will it survive, when you do the check, it will pass the check. So everything is confirmed. If it doesn't pass the check, then you know that there is no half majority, right? So everything is proved. Is this clear? So the algo outputs the half majority or none correctly. And what is the time complexity? So this we have seen by halving and repetition, it's order n. Okay, so this is the linear time algorithm to find half majority on unstructured array, right? It's not only unsorted, it cannot be sorted. Still you can compute half majority in linear time. Any questions? But this is not the pseudocode that the student said. It's not one scan, right? How many scans are these? Oh, just two. 2 is very little. These are log n scans, because you are halving and then first you did n, then you did n by 2, then you did n by 4, so these are log n scans. Sometimes for extremely silly devices like smart card machines or even simple phones, you want to even optimize the number of scans. Just order n may not be good enough, because it is looking at a lot of data, but it has very little memory or capacity. So you want to do this really in one scan. One scan basically means that it's a stream of data which is never stored. So there is an infinite stream coming, let's say, from a satellite, and you just look at one bit by bit or structure by structure, and that's all you know. You don't know the whole data, and still you want to compute majority, half majority. So how do you do this in one scan?
Comparing with the previous element that survived the page.
So for applications where input is a stream and you cannot store everything as an array and go back and forth again and again, what you have to do is you have to get inspired from the this algorithm that we just discussed quickly and write it as a pseudocode already suggested. So what you do is you keep a count and a guess for half majority. Okay, you keep a current guess of half majority, and then when things go wrong, then you change the guess. Okay, and whether things have gone wrong, that will be given by the count. Okay, so you keep a guess of, so the pseudocode is very simple, but let us just inspire that a bit so that you can understand what happened in the pseudocode. So this will be idea 3. So keep a count variable, do one scan, update, and based on a condition, you will keep updating the count variable. Keep guessing this half majority x. And then ultimately verify. Okay, so we have to make sure that this guess of x that we are making, two things should be true, that if it exists, then you should have it. And only one thing actually, if it exists, you should have it. That's the only invariant you want in your guess. If it doesn't exist, you don't care, because whatever you are guessing, anyways in the verification process, it will be rejected. Right? So you need only one invariant in this pseudocode, that your guess should be correct if there is an x. And if there is no x, you don't care. You can make any guess, it's fine. Ultimately, it's rejected anyways. So let's jump to the pseudocode for this. So count is 0. And x is just declared. It has currently you are not guessing anything. Then the stream starts of data. So as you look at elements, what you do is, So you are reading the stream here. So this will be the important part. So when you are at a stage where the count is 0, then you actually have no guess. So whatever you will see, you will just assume it to be half majority, guess it to be half majority. So what you have seen right now is AI. So let us just set X to be this AI. And since you have seen it once, you can increment the count. In the else case, now you are in the case where count is already positive, so you have a guess of half majority X. Right? X is storing some data value. So at this point, you should check whether the new element in the stream that you are seeing, if it is equal to your guess, then what happens? Then you increment. Your guess is better, gets better valuation. And if it is different, then you should minus. Yeah. So let me just say count minus. And if X is equal, then count plus. And that is the end of the data stream. Okay, so now you have seen the whole data stream, and if this half majority X existed, then you should have X at this point. But you have to verify, because maybe this is a fraud. So you verify that. So if the frequency of X in A is greater than n by 2, then you return X. Else you return nothing. Okay, so that's the one scan of the data stream. Is that fine? Do you believe in this algorithm? So if you don't believe, then you should go home and check this. It builds on the properties we developed in the previous theorem. But this is a much more clever implementation. Sorry? I cannot hear. What? What line are we at? Instead of checking for frequency, you want to say? So this will be 2 scans, yeah. Count greater than 0 is the check. Yeah, so actually he may be right. So let me just make an edit. One has to check this, that you can replace it by count positive.
No, sir, it won't work. If there are odd number of elements, let's say 7,
Yeah.
then some
Yeah, so I'm not confident about this.
then it will return last element, sir.
Hmm. Yeah, so then the problem is that then this doesn't work for a stream. It's 2 scans. It's not 1 scan. No, no, no. In a stream, you can compute the size. You can keep a size counter. That is fine.
I'm saying if we are claiming that we can do it in a single scan,
Yeah.
then you can just take an example in which, let's say, we initially have 100 elements. You got the half majority of 100 elements, then we have 100 more elements coming, and all of them have the same elements. That's
Yes.
101 element.
Right.
All of them have-
Sure, yeah.
So in this case, the half majority changes.
Yeah, so you are saying that one scan is impossible.
Yes, sir.
So next possibility is 2 scans.
Like we'll always have to make a verification.
Yeah, that's what I think. I don't think the modification is this simple. You cannot just check count here. So let's reverse this. So okay, so let's record that. So I guess when there is a half majority guaranteed, then it will find in one scan. But it is not, the algorithm doesn't know whether it has found correctly or not. Okay, so algorithm may be wrong because there may not be a half majority. But when there is a half majority, it's finding in one scan.
So even when there is a half majority, it is not possible to.
Possibility is given in the previous slide. So the algo finds half majority in a stream in order and time. And the algo can verify in 2 scans. Or in an extra scan. So if you want a verified answer, then you have to do a scan again. But if you don't want verification, you are already confident, then this is one scan algorithm, linear time. Okay. So if the lecture has confused you even more, then you should check everything. So basically write the invariant. What is the invariant in this pseudocode? And based on that, there is an immediate proof of correctness. Okay, so here key thing is the invariant actually. What is the invariant? Invariant is half majority is unique, it's X, and that will appear as a guess at some point in this pseudocode. And once it appears, it never changes. Okay, that's the invariant. So it is guaranteed that after n by 2 steps, X will be your guess, and it will remain till the end. Remain so till the end. Okay, so that's the invariant. Once you have the invariant, you have the proof of correctness immediately. So that's what you have to check in this pseudocode. It's a very clever pseudocode. So that is one thing. The other clever algorithm we will see, which will be extra clever, is for the problem of multiplication. So how do you multiply numbers? So when I say multiplication, I'll always mean integer multiplication. Okay, so here the input is 2 numbers. So let's say X is given as an array and Y similarly. So it's like this, 0 to n minus 1 entries with the labeling of this is the least significant bit and this is the most significant bit. Okay, this is the orientation we'll use in the next class. So you are given, so these are bits. I mean, integers you can write as bits. These are positive integers, say. So these are the binary string is given in two arrays, x and y, n-bit integers. In the output, you have to give the product. Okay, so you have to give the array for the product as a string, binary string. So what will be the idea 0 here? What is the school pseudocode?
Convert it into decimal and then multiply and then convert to binary.
But what is, okay, so what is the complexity of that? How do you learn to multiply in school? Digit by digit you multiply, so it's a n scan process, right? So n scans means that it's n square time. So we will see much faster than n square next time. Have you seen this algorithm, better than n square multiplication? Yeah, so we'll see that next time. It's also used in hardware. Okay, thanks.